The wireless rain detector consists of two ESP32-C3 Super Mini-modules that communicate wirelessly using Espressif's fast ESP32 protocol, which allows for direct connections without a router. One ESP32 is configured as a client. It connects to the rain detector module and a separate humidity and temperature module. The second ESP32 is configured as a server. At regular intervals, it receives messages from the client about the status of the rain detector and the current temperature and humidity values. The server is connected to a buzzer and is used to sound various alarm states. The ESP32 server can be configured using a dedicated Android application on a mobile phone. The Android application communicates with the ESP32 server using Bluetooth. Both the ESP32 server and client are directly powered from the 5V DC USB-C power connector that is mounted on the ESP32-C3 Super Mini board. The rain detector module connected to the ESP32 client requires 12V DC to operate. Therefore, the ESP32 client module is mounted on a dedicated ESP32-C3 Super Mini expansion board that includes a step-up boost converter, used to boost the voltage up to 12V DC. The boost converter is controlled by the ESP32 client module using a 35 kHz PWM frequency, controlled by a 5 kHz PID control loop to maintain a stable 12V DC output. The chip antenna soldered on the factory ESP32-C3 Super Mini-module as used in this project is prone to cause interference with the ESP32 chip because of its close proximity to the chip. Therefore, a modification has been applied by removing the chip antenna and replacing it with an external antenna. The cable for the external antenna has been connected to the feed point of the original antenna. The shielding of the antenna wire has been soldered at the back of the ESP32 circuit board by grinding off a piece of the solder mask covering the ground plane directly underneath the antenna feed point. When measuring the power consumption of the client, including the boost converter, when the rain detector is idle, it consumes approximately half a watt. When activating the rain detector, which switches are in the internal relay that is mounted inside the rain detector, the client module consumes approximately 2 watts. When the boost converter is delivering the maximum required power when the rain detector is active, after about 5 minutes the inductor has reached a temperature of about 32 degrees Celsius. This is way lower than the overall temperature of the ESP32-C3 microcontroller. Starting the Android application when both client and server have been powered on. If Bluetooth is not enabled on the phone, the app asks permission to switch Bluetooth on. With Bluetooth enabled, the app is starting a scan. When an ESP32 module is found that is using the correct Bluetooth settings, the app will automatically connect. Once connected, the app is sending a message to the server requesting its settings. The server responds with its Bluetooth MAC address, the humidity alarm threshold value, and the state of the rain detector and humidity buzzer. By default, the server will start with a humidity level of 65%, and both the rain detector and the humidity buzzer activated. The application will update the humidity value and its buzzer slide switches accordingly. The client will check the state of the rain detector every second. The temperature and humidity measurements will be requested from the DHT module every 10 seconds. The client will send the information using the ESP32 protocol to the ESP32 server. The server will forward the messages to the phone's app. The temperature and humidity measurements will be displayed in the app when received. The rain detector messages will be checked by the app and will only be displayed when the rain detector is active, when rain has been detected. The rain buzzer can be muted by pressing the app's rain button. The rain detector will return to idle when the rainwater is removed from the sensor. To activate the humidity alarm, let's lower the threshold to a value that is below the active humidity level. After pressing the Submit button, the server will update its humidity threshold value. When the first measurement is received from the client, the server will sound the humidity alarm. The alarm can be disabled by pressing the humidity button in the app. Or reset the alarm by updating the threshold level. Every time the Submit button is pressed, the app will store both the MAC address and humidity threshold level to the phone's memory. The app will automatically use the data stored in the phone's memory to fill in the MAC address whenever the app starts, only allowing a connection to that specific ESP32 server. To allow the app to connect to another ESP32 server module, first clear the MAC address from the entry field and click on the Submit button to clear it from the phone's memory. The next time the app is started, it will automatically connect to the first module it finds. When power to the ESP32 server is lost, the app will detect it and clear all the configuration information it had stored for that session. When power is restored, it will automatically connect to the app, which will continue to receive the information sent by the server. When power to the ESP32 client is lost, it will be detected by the server within 5 seconds. The server will sound a short beep every 5 seconds once the ESP-NOW connection to the client is lost. When power is restored and the ESP-NOW connection is restored, operation continues as normal. The overvoltage protection of the client's boost converter is set to 13 volts, which is quite tight. It can therefore be tested by quickly switch the relay of the rain detector on and off. When the load on the boost converter is released in such a manner, it can cause the booster to overshoot its set value and trigger the overvoltage alarm. The client will automatically switch off the boost converter. An undervoltage alarm will automatically be triggered when the voltage drops, but it will not be displayed if the booster shutdown was caused by overvoltage protection. An undervoltage alarm alone will most likely be caused by too much power consumption or a short circuit on the 12-volt output. This will cause the polyfuse to trip and cut the power to the booster. Disconnect and reconnect power to the client in order to restore the booster functionality.